Hey, this is Mr. Ward, and this is a little walkthrough of the beginning of 8.3, which is about methods for proving triangles are similar. So first of all, there's a postulate. So here's what it says. If there exists a correspondence between the vertices of two triangles such that three angles of one triangle are congruent respectively to between the vertices of two triangles such that three angles of one triangle are congruent respectively to the corresponding angles of the second triangle, then the two triangles are similar. That's angle, angle, angle. Basically, this is a fancy pants way of saying if the corresponding angles are all congruent, then the two triangles are similar. Okay, and we're going to be using that postulate as a foundation for proving that triangles are similar, not congruent. Please keep that distinct. So just like we use side, 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 angle, hypotenuse, leg, and angle, angle, side to prove congruency, we're going to be using some variations of angle, angle, angle. So the first one is angle, angle, which is related to the no-choice theorem. If you recall, if you know that these two angles are congruent to these two angles, then this third angle has to be congruent to the third angle because there's only 180 degrees to work with in a triangle. So if there, Theorem 54, if there exists a correspondence between the vertices of two triangles such that the two angles of one triangle are congruent to the corresponding angles of the other, then the triangles are similar by angle, angle. And the angle, angle just forces angle, angle, angle. Which goes back to our postulate. So this relates, of course, to the no-choice theorem that was back on page 286. Okay, then there's another one. So if instead of focusing on angles, there's one that's like side, 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 but there's a little distinction. See the little squiggly wiggly there? That's a tilde, which is a symbol used in geometry for similarity. So if the corresponding side, so here's AB and AD. If AB over AD equals BC over EF equals AC over DF, if those ratios are all the same, this forms a proportion, then these triangles are similar. Now, then there's another one where if you know an included angle is congruent, so here B and E are congruent, and you know that there's a ratio that works for the two sides that are on the either side of that angle, then you have enough to prove that the triangles are similar as well. This is side angle side similarity, not congruency. So Theorem 56, if there exists a correspondence between the vertices of two triangles such that the ratios of the measures of two pairs of corresponding sides are equal, and the included angles are congruent, then the triangles are similar by side angle side similarity. So here we've got AB is to DE as BC is to EF, and the included angle, which is B and E in both respectively, are congruent, then these triangles are similar. Okay, and then it walks through a few sample problems. So here we've got given A, B, C, D, that's a parallelogram. We want to prove that triangle BFE and CFD are similar. Okay, so we've been given the parallelogram. We know that AB and CD are going to be parallel, and that sets up some alternate interior angles for us. So CDF is going to be congruent to angle E because they're a pair of alternate interior angles. And then we've got DFC and EFB are congruent because they're vertical angles. So now you've got two angles, and by angle, angle, we can now say that triangle BFE and triangle CFD are similar. Okay, here's one that looks a little messier. We got angle MET is congruent to RST. We know that ST is perpendicular to MR. Okay, and we're trying to prove that MET, this left triangle, is similar to RST. So we've got a couple of givens, but STM and STR have to be right angles because ST is perpendicular to MR. And so that means that we've got angle, angle, because this angle and this angle are congruent, and MET and RST are congruent. So once again, we've got a proof with angle, angle similarity. Okay. And example 4, sample problem 4, we've been given KH as the altitude to the hypotenuse of GJ of GHJ. And we're supposed to prove that KHJ, this is KHJ, is similar to HGJ, which is the big triangle. We could also prove, so KHJ, we would actually be able to prove that not only is KHJ, but KGH is also similar. We have 3 similar triangles here. So we've got the given. We've got that HKJ is a right angle because KH is an altitude, and that makes a right angle by definition. And we know that JHG is a right angle because the hypotenuse is the opposite to the right angle. And so that we've got 2 right angles that are congruent. So angle HKJ and angle JHG are both right angles. And angle J is shared by both triangles. So it is itself. So we got angle, angle. This right angle and this right angle are congruent, and J is itself. We'd be able to prove the left side triangle works for the big triangle as well by angle G being congruent to itself and those right angles, and by substitution or transitive property, we could prove that all 3 triangles are congruent. There's some other ways, similar. And I apologize for that bumble. But here we go. We got this one, example 4. So if the 2 points are one on each leg of the isosceles triangle, so from 2 points, one on each leg, perpendiculars are dropped to the base, the triangles formed are similar. So you can see we dropped from S, and we dropped a perpendicular from S, and dropped a perpendicular from V down to O and P, and these are going to be right angles here. So we've got MTR as isosceles, so that means this side is congruent to this. It also means angle M and angle R are congruent. Well, this is going to be pretty simple to do. You can work through all of this, but we know it's isosceles, so M and R are congruent. And VOM and SPR are right angles and therefore are congruent as well. So you've got angle, angle. Okay. And I'm going to stop, and then I'll talk a little bit through some of the problems that you've got to work on this.